I am Christine, and I'm going to be talking about hydrothermal fluids on Europa. So, you've heard a couple talks about hydrothermal systems already, and this is an ocean world session, so I'm sure I'm not blowing anybody's mind when I suggest that there might be hydrothermal systems on ocean worlds. And in particular, you might have heard about this from the Cassini mission when it flew through the plumes of Enceladus and actually detected for the first time observational evidence that hydrothermal processes could be occurring on ocean worlds. And this in particular was an interesting result. So they found, just kidding, mixing up my buttons. So they found molecular hydrogen, which we think in the high abundances that it was detected on Enceladus must be a result of hydrothermal chemistry. And they not only found it, but they found it in disequilibrium concentrations with methane and carbon dioxide, such that you get a high chemical affinity or an abundance of free energy for this reaction, methanogenesis, which is exciting. It's a big astrobiological buzzword because methanogens, they use this reaction to fuel themselves as a metabolism on Earth. So, how does this work exactly, right? So we have hydrothermal systems, somehow they're providing stuff that's fueling energy for life. How exactly does this happen? Well, you have some rock, it has this stuff in it, you pour some water on it, you heat it up, and it starts outgassing interesting things like hydrogen, methane, carbon dioxide, those methanogenesis ingredients, as well as other things. And that's all well and good. Everything in this hydrothermal system is in equilibrium. But then, once you mix it with the cold ocean water that has a totally different chemical composition, they clash, and you get disequilibrium. And in particular, we think in the oceans of these icy moons, you can actually be getting molecular oxygen. So you can make oxygen in the icy surface. Radiation breaks apart water molecules there. And if your surface is geologically active, which we think they are in ocean worlds, then you can actually take this oxygen and deliver it into the ocean. And then you have all these reduced species coming up from your hydrothermal fluids. You have oxygen floating around in the ocean and disequilibrium for redox reactions. So life takes advantage of this disequilibrium. It extracts energy from that to push the system back toward equilibrium and uses that energy to sustain itself as a metabolism. So could these things be happening on Europa? We've seen evidence for it on Enceladus already. The issue with Europa is that it's larger, we think it's more complicated, and we know nothing about it. So how do we deal with something like that? We consider all of the possible scenarios that it could be falling under. So we know a lot about hydrothermal systems on Earth. We think we know something about how they might be working on Enceladus, maybe on Io too, which is not hydrothermal, but at least it's volcanically active and in the Jupiter system. So we can apply all of these different geochemical constraints from all of these other bodies and say, most likely Europa's falling somewhere within this parameter space of all these other analogs, and look at exactly how these different parameters combine to affect hydrothermal geochemistry, potentially, and energy availability on Europa. So we can start by making these lovely activity diagrams. So let's pretend like we have a black smoker on Europa, 300 degrees, the European seafloor pressure 1500 bar, and we don't know what the pH of this black smoker fluid is, we don't know what the oxidation state is, so we're just gonna let those vary, and we're gonna look at generally, for carbon at least, what does the parameter space in that hydrothermal fluid look like? So we see we can get all of these different things, it depends on these parameters, and now we can try to set some reference points to try and see if we're near this reference point, what does our fluid look like? So for pH, we can calculate what neutral pH is as a function of temperature, plot that on here, and maybe say Europa's probably, I don't know, within 2 log units on either side-ish of neutral pH. So how would the speciation of carbon change as you move from higher pH to lower pH around that pH neutral point? And same thing with oxidation state. So the FMQ buffer, what is happening? This is very dramatic. The phthalate magnetite quartz buffer approximates redox conditions in ultramafic rock on Earth. So we think there's ultramafic rock in some of these hydrothermal systems on Earth. It's not necessarily, being buffered by these minerals, but it's like around what you would predict the, it's fine. It's around what you would predict the hydrogen activity to be if it were being buffered by these minerals. So let's plot that on there. Again, it's temperature dependent. At 300 degrees, this is where it falls. And let's say maybe Europa is at the FMQ buffer. Maybe it's more reduced compared to that. Maybe it's more oxidized compared to that. How would that affect the distribution, the speciation of carbon there? And then let's start playing around with the parameter space. So we've seen that at 300 degrees, this is what it looks like. If we then change the temperature, so let's make our hydrothermal fluid colder, you can see that these more oxidized species get pushed out to 0 degrees when you only have methane, and vice versa. When you make it hotter, you're pushing CH4 out and getting more oxidized species. So that tells us if you have hotter hydrothermal fluids, then maybe you have more oxidized species unless you're really, really reduced. If you have cooler hydrothermal fluids, maybe you have more reduced species unless you're very, very oxidized. So now I'm going to flip the parameter space around on you a little bit, and instead of fixing temperature and letting pH and oxidation state vary, I'm going to do the opposite. So I've fixed the oxidation state at this FMQ buffer reference point. Here I fixed the pH at pH neutral, and now we're going to vary pH one at a time and see what happens. And you can see that as you move to more alkaline pH values, all of these charged species like bicarbonates and carbonates start showing up, especially at higher temperatures. So essentially, pH's job, is to control the abundance of charged species in your fluid. That's its primary role. So this is a lot of lines, but just bear with me here. So this is what I showed you before, right? We decided as we move down here, as we move to more alkaline pH values, you get more charged species. And now we're going to vary oxidation state one at a time and see what its general effect is. So if we're at FMQ and we move to more oxidized values, you can see that methane, of course, is getting pushed out there. And it looks like at this oxidized reference point, the role of pH is really dramatic, right? These plots look drastically different from pH neutral to pH neutral plus 4. Whereas if you're more reduced, they look exactly the same. So pH and temperature have less of an effect when you're at more reduced fluid values. When you're more oxidized, the effect of pH and temperature is much more dramatic. So that's interesting, right? We have some idea of maybe how these different parameters could be affecting the hydrothermal fluid composition on Europa, but let's tie this into astrobiology, because this is an astrobiology conference. So how do we do that? Well, methanogenesis, buzzword again. We looked at it on Enceladus. Let's look at how it might be working on Europa. So I showed you on Enceladus they calculated the free energy, the chemical affinity for this methanogenesis reaction. The way to do that is by calculating this reaction quotient Q, and for that you need the ratio of methane to carbon dioxide, and you also need the activity of hydrogen. So just to explain this a little bit more, this guy I've put in orange because this we're assuming is controlled entirely by those parameters that I was varying in the hydrothermal vent fluid. So we're not assuming respeciation in the ocean yet, we're assuming this ratio is set by our hydrothermal vent. Hydrogen, on the other hand, we're assuming is set by the parameters of the global ocean. So again, you have this hydrothermal CH4 to CO2, it's mixing with hydrogen in your ocean. They're totally different chemical properties, they clash, they create disequilibrium, they give you energy for methanogenesis. So the issue here is that we have no idea what the activity of hydrogen is in Europa's ocean, but we can at least try and maybe get some upper limits and lower limits. So I'm going to assume that the ocean is probably not more reduced than the hydrothermal vent fluid. So the most reduced it can be is at this FMQ plus 2 buffer that I showed you before. On the other hand, the more oxidized it can be is much, much lower than that, right? So I mentioned that you can get radiolytic oxidants from your surface being delivered to your ocean. This paper down here has actually constrained how many of those oxidants might be in Europa's ocean. So we can assume, as a lower end member, that oxygen and hydrogen are in equilibrium in this 0 degree ocean. And because you have a lot of radiolytic oxidants, you have very, very little hydrogen. And we'll assume that our hydrogen activity on Europa is somewhere between those two end members. As you can see, this varies drastically. Obviously, if you have free energy below 0, that's not good for life. But specifically, you want to be above this reference point. So biologists on Earth have constrained the amount of energy you need from a metabolic reaction to actually sustain life. It's about 10 to 20 kilojoules per mole. It's right here. So as you can see here, if you want to meet this requirement, you need to be up in this space up here. So your ocean fluid needs to be pretty reduced, maybe slightly more oxidized than the vent fluid, but still it needs to be in this region over here. Yeah, so reduced ocean, good for methanogenesis. Oxidized ocean, bad for methanogenesis. Does that mean if we have an oxidized ocean, at FMQ and pH neutral, that's the end, that methanogenesis, the affinity can't change if we, again, start varying these parameters? No. So let's look at what happens. pH, obviously, we would expect not to have an effect, right? Because we said that controls the abundance of charged species. It has nothing to do with the CH4 CO2 ratio, at least not if we're not considering respeciation. Whereas oxidation state, we said, does affect methane and CO2. If you're more reduced, you get more methane. If you're more oxidized, you get more oxidized species. And you can see this, right? So this line shifts up and down ever so slightly as you change oxidation state. But the takeaway is the same. You still need to be in this more reduced region in order to be above that yellow line. So does that mean that if we have a more oxidized ocean, it's dead, there's no life? No, because we can also consider aerobic reactions. So let's say we have life that's using those radiolytic oxidants to oxidize methane. Well, we have constraints, again, on the amount of oxygen that might be in Europa's ocean from this paper here. This is assuming hydrothermal processes are eating some of that oxygen. This is assuming the oxygen is just building up and not really being reduced. But even so, even at these low levels of oxygen predicted in this paper, you still have tons and tons of energy for aerobic methane oxidation. And in fact, it's well above, again, this 10 to 20 kilojoule per mole level that you need to be at in order to sustain life. So this looks really good. But again, I've fixed the oxidation state, I've fixed the pH. We have no guarantee that Europa's hydrothermal fluid actually looks like that. So what happens if we vary that parameter space? Well, again, we've decided oxidation state changes your CH4 to CO2 ratio. So we were here before. As we move to more oxidized conditions, the energy shifts down. As we move to more reduced conditions, the energy shifts up. But even so, again, you're still like well above 400, 300 kilojoules per mole, well above that 10 to 20 kilojoule per mole level that you need to be at in order to support life. So good news for methane oxidation. So summary here, right? Methanogenesis, you need to be above the yellow line. If you have a very reduced ocean fluid, that's good news. You meet that. If you have more oxidized fluid, that's bad. And it doesn't look good for methanogenesis, but that's fine because even if you are at more oxidized conditions, like here, you can still use aerobic oxidation, like methane oxidation, to support life. So in general, our hydrothermal parameters, even though they change drastically the composition of your hydrothermal fluid, and they do change the amount of energy, the amount of life you can support, absolutely, you still can support some life from aerobic reactions from methane oxidation regardless. And I just wanted to add that this is also great for Europa Clipper, which is going to go up hopefully sometime in the 2020s and measure the composition of the ocean from the plume. So we can take those measurements and trace them back to these kind of models to figure out what kind of hydrothermal processes might or might not be happening on Europa and how much chemical energy might be in the ocean. And with that, I will take questions.
Okay, so we have time for one or two questions. And if anybody's cell phone, we have some feedback going on. So the front row, I hear. Does anyone else hear that?
It's the session next door.
Oh, okay, never mind. Carry on, okay.
So if there's a measured disequilibrium, that might suggest that life didn't use it. So is there a way to use this modeling to calculate the maximum amount of measurable disequilibrium that still allows for some life to have been around?
Yeah, so this is a big question, and this is something people raised with the methanogenesis chemical affinity also. Like, if there's all this free energy on Enceladus, why isn't life using it? And we don't really have this constrained well enough because we don't know how much life could be on Enceladus, and based on that, we don't know how much of this, how much it's going to drive the system toward equilibrium. So maybe without life, you would have even more chemical affinity than what we actually measured. We don't know. Something I would like to do on Earth actually is look at, in systems where we know there are methanogens, how much free energy is there for methanogenesis? Is it zero, or is it still some positive amount? Because you still, if it's zero, that kind of tells you the system might be in equilibrium. You can't really support more life, but is that necessarily true? It would be really interesting to compare how we know this works on Earth to ocean worlds.
All right, we will keep moving along. Thank you very much. One more round of applause for Christine.